In this video, we present our paper, RSL-Net, Localizing in Satellite Images from a Radar on the Ground. Current approaches to vehicle localization typically assume the existence of a prior sensor map, and that the prior map is compatible with the onboard sensor. For example, localizing an onboard camera against a prior map of camera images. The prior sensor map can become unreliable due to scene appearance changes. Typical solutions include collecting multiple experiences across various scene, weather, and lighting conditions, or learning some kind of domain transfer, for example, from daytime to night images. In extreme scenarios where the prior sensor map is completely unusable or missing, off-the-shelf overhead imagery offers an easily accessible fallback solution. In particular, frequency-modulated continuous wave radar is a long-range sensor that is invariant to weather and lighting, and the radar data can be displayed in a bird's-eye perspective, making it ideal for our task. Shown here are Cartesian and polar representations of the radar data. Specifically, given a coarse initial pose estimate from place recognition, we wish to solve for metric localization, namely compute an SE2 pose for the vehicle. This is done by comparing live radar data against overhead imagery queried at the initial pose estimate. Shown here is radar data overlaid on top of Google satellite imagery using metric ground truth. It can be seen that there are strong correspondences between the aligned radar and satellite images that are useful for pose estimation. This problem is nevertheless very challenging. First of all, radar images and overhead images are starkly different modalities of data, and it's not immediately clear how they can be compared for pose estimation. The ephemeral parts of the scene, such as cars and pedestrians, may exist in the live data, but not in overhead imagery, or vice versa. Finally, due to occlusions and its sensing nature, the radar has a limited field of view and only observes a small region of the scenes captured by the overhead image, making pose estimation potentially ambiguous. We present Radar Satellite Localization Network, RSL-Net. Specifically, given a matched pair of radar and satellite images with sufficient overlap but an unknown SE2 pose offset, we generate a synthetic image that has the same appearance and observed scenes as the radar image, but is pixel-wise aligned with the satellite image. In this process, we also infer the heading offset between the radar image and the satellite image. Finally, the rotational aligned radar image and the synthetic image are projected to a joint embedding where their translation offset can be found. Naive image-to-image transfer methods, such as pix-to-pix, would seek to learn appearance transfer on the satellite image to synthesize the appearance of a radar image. However, this can be problematic due to the limited field of view of the radar, as mentioned earlier. Shown here are two radar images taken 15 seconds apart from each other, pixel-wise aligned with satellite images using ground truth. Though the overlapping regions of the satellite images are identical, the radar scans appear significantly different because of occlusion. When we apply naive image-to-image transfer, there is no guarantee the synthetic image will end up highlighting regions of the scenes observed by the actual live radar image. To solve this issue, we learn image generation that is conditioned on both the satellite image and the radar data. However, this is not trivial as the satellite image and the radar image are offset by a translation and a rotation. Standard CNNs are only equivariant to translation but not to rotation. Therefore, it's not immediately clear how the network can fully take advantage of the mutual information between the two inputs. To handle the issue with equivariance, we seek to first infer the heading offset between the radar image and the satellite image. Based on the initial estimate, the radar image is rotated many times with small increments, both clockwise and counterclockwise. This produces a stack of rotated radar images. Each rotated radar image from the stack is then concatenated with the satellite image along the channel dimension. This forms a stacked tensor that is fed to the rotation inference network. The network outputs an image by taking the softmax from the input stack, which will be the radar image rotation-wise aligned with the satellite image. Once we have inferred the rotation offset, we can learn an image generation condition on the satellite image and the rotation-aligned radar image. Here, the two inputs are offset only in translation, which standard CNNs are inherently equivariant to. For image generation, we use a standard encoder-decoder architecture with 9 ResNet blocks at the bottleneck. The generator network outputs a synthetic image with the same appearance as the input radar image, but is pixel-wise aligned with the input satellite image. Previously, during rotation inference, we have discovered the heading offset theta, but we still need to compute x and y. Here we have created a synthetic radar image pixel-wise aligned with the satellite image. The synthetic image and the rotation-aligned radar image are then projected to a joint deep embedding where their translation offset can be found by finding the maximum correlation from a predefined XY solution space. In practice, this can be done very efficiently in the Fourier domain. Shown here is the overall architecture of RSL-Net. We use UNet for learning the embeddings for pose estimation. The following clip provides a graphical illustration of data flow of our pipeline at inference. From a stack of rotated radar images, we infer the heading offset by comparing each against a satellite image. Using the rotational aligned radar image, we then generate a synthetic radar image pixel-wise aligned with the satellite image. The synthetic image and the rotational aligned radar image are then projected to a joint deep embedding, where their offset in translation is found by correlation maximization. We validate on 2 radar datasets with GPS solutions. To simulate a coarse initial estimate good enough for place recognition but not metric localization, we add large artificial offsets to the GPS solutions at each frame when querying for the satellite images. We achieve an error of a few degrees in theta and a few meters in x and y on the Robocar dataset, which features an urban environment. Our errors are higher on another highway dataset we collected due to the lack of geometric structures useful for pose estimation. Finally, this video shows the estimated pose compared to the true trajectory at each frame on the test set of the Robocar dataset, as well as the output images at various stages of our network. Thank you for watching this video. If you're interested in localization using overhead imagery, check out our recent paper at RSS. To learn more about radars, please scan the QR code to follow our research at the